This certainly seems like a strange question to lead with on the first day of Calc 3, because there were like two other calculuses before this one. Don't we know what calculus is? Now, the difference is y'all weren't in my calculus class, so we want to make sure we come from different calculus traditions. We want to make sure that we can get on the same page. We want to see what I want for a mindset when it comes to calculus. Here's what I think of calculus. I think of calculus as the study of infinity. That's like super broad to the point of kind of being useless, which is probably why I like it. Calculus is the study of infinity. Now, when I talk about the study of infinity, I'm not just like thinking about infinity, like in a philosophical sense, or working with infinity in kind of an engineering sense. I'm talking about rigorous mathematical study of infinity. So we want to apply some rigorous rules to this stuff. So what kind of rigor can we put around the study of infinity to make things consistent and make sense? The surest way you can tell that calculus is an engineering class, despite the fact that it says math right at the front of it, is that a lot of times calculus is described as the mathematics of change, equally broad and useless, but very revealing as an engineering discipline. And that's why we have calculus. Later on, some of you are going to become math majors, and you're going to take a class called real analysis, and you're going to be like, oh, dude, isn't this just calculus? And the professor will be like, oh, no, calculus was analysis, but for engineers. So we got to think about the story of calculus and what is the central tension in the story of calculus. And the central tension, in my view, of the story of calculus is the boundary between the discrete and the continuous. In terms of infinity, the countable versus the uncountable. A discrete variable might be the number of people in this class. That's a countable set, not an infinite set, but a countable set. There's 1, 2, 3, 4, 5, 6. That's why we call it countable, because we can count them. A continuum doesn't have that. A continuum, I can't just say, here's the first one, here's the next one. In a continuum, there is no next one. So for example, if at one point you were 5'2", and then later on you were 5'3", you were necessarily every height in between. There was no next height after 5'2". Because whatever you pick for the next one after 5'2", there was something in between. Moreover, there was an uncountable infinity in between. So we have a discrete set and a continuous set. I see calculus as the study of infinity. I see the central tension of calculus as us trying to rigorously understand the discrete versus the continuous. So if I talk faster, that could be like the first video. I'm trying to make math TikTok. Just instead of doing like a one classroom or one class that takes like 17 weeks where we have to like meet, what if I could just do this in a bunch of TikToks, a bunch of 1-minute videos? Do you want to watch a 60-hour movie or a 60-minute movie? 60 hours, that's a teacher for you. A 60-minute movie or 60 1-minute movies? Anyway, so that would be my first one, hashtag math talk, which is actually hashtag math talk. That's part one, central tension. What are we studying in calculus? And what is the central tension that we have to do? Number two, the framing device. This is where it might start looking familiar. The framing device that we use to tell this story of infinity are the two big questions that we deal with in calculus. The framing device that we want to use to explore this story are the two big questions of calculus. Oh, TM, trademark. The two big questions, trademark of calculus. I don't think there's a trademark for that. I capitalized it, so it must be a thing. I'll be revising my OML, my Open Math License, Open Math License 1.1. So the two big questions, trademark, of calculus. What is the slope of the line tangent to a curve? At a given point. I called it the two big questions. I didn't phrase it in the form of a question. I'm not very good at Jeopardy. The other big question of calculus is the area under a curve and above an interval. Let's draw a picture of these two. A picture in this case is not necessarily worth 1,000 words, but quite a few. What we're talking about is if we have some kind of curve here, and we have a point on that curve. So we have a line tangent to the curve at a given point. We want to know what is the slope of that tangent line. At this point in our mathematical careers, we know the answer to this. It's the derivative. The derivative evaluated at that point. Derivative evaluated at that point. Then we spend a lot of time figuring out what we can do with it. Linear approximations, instantaneous rate of change, cool stuff. The other part of the framing device is what is the area under a curve and above an interval. The other big question, what is the area under the curve? I like to add the part under the curve and above the interval, an interval. We know the answer to this question as well. That's just going to be the definite integral of f of x to x over the interval from a to b. two big questions. This is our framing device for exploring the story of calculus. I'm probably gonna have to talk faster. I'm just gonna speed myself up. I don't want to record this again. I'm also gonna need like a distinctive opening. Hello, my friend. And then when I'm explaining this stuff, I'll just use my picture like circles. That's good. Now, you might be looking at this point and saying, dude, you just wrote on the board multivariable calculus and vector calculus. What's this single variable calculus? Moreover, I'm a little bit insulted that you felt it necessary to limit us to functions. You know, parametric equations and stuff like that. Here's, as a side note, 2.5. Why calculus 3 is the easiest of our three calculus classes. Calc 3 is the easiest calculus class because these two questions are the same. All we're doing is putting more variables. So Calc 3 is the same questions. What's the slope at a point? What's the area under a curve? Just adapted to more than just two variables. Instead of just x and y, what does it look like when we have x, y, and z? What does it look like when we have a function of two variables? What does it look like when we have an equation in three variables? So Calc 3 we have the same questions with more variables. That's why Calc 3 is the easiest one, because you already have the thinking in place. You already have your derivative thinking and your integral thinking in place. You just need to adapt it to functions of more than one variable, or equations with three variables, or even more variables. Think back to algebra. Remember how algebra was so simple because you realized that algebra is just arithmetic. All that time you spent learning how to do arithmetic, you're doing the same operations all throughout your algebra class. You learn how to multiply numbers like 23 times 17 in a phenomenally stupid algorithm. And then you went on to polynomials and you did the same thing. Unfortunately, that was probably hidden from you because you were taught, what's the four-letter word, starts with F, multiplying polynomials? First, outer, inner, last. That's the same thing as the algorithm that you learned in 10th grade whenever you learned to multiply two-digit numbers. It's just the distributive property. For some reason, we kept that information from you because, I don't know, we're jerks. So that's what we want to think about. Same two questions, upgrading to more variables, throwing more variables. Any questions? That's like a 1-minute video. Calc 3 is easiest because it's the same thinking with more variables. How do we use the framing device? How's everybody okay? If you're wondering, man, he talks a lot. Is this ever stop? No, it never does. It's just more of this. If you're like thinking, that's awful, you are correct. Which is weird because my philosophy as a game master is like the opposite. If my players had fun, then I had fun. But in the classroom, it's like exactly the opposite. Like, well, I'm having fun. All of your students are suffering. Yeah, but I had fun. Don't you want them to have fun too? They can have fun if they want. I'm just kidding. You're not allowed to have any fun. I'm just kidding. I can't control that. How do we use the framing device? A couple of different ways. Remember, calculus is the study of infinity. Where's infinity play into this? Where's this difference, this conflict between the discrete and the continuous show up? Let's take this first one, because we do calculus phenomenally backwards. We got the two big questions, one complicated, one pretty simple. Let's do the complicated one first. Jerks. We approximate the tangent line with the secant line. We approximate the tangent line with a secant line. So we got this tangent line that we're trying to figure out. But we have a problem. We have one given point. But when we calculate the slope is change in y divided by change in x. I can't do change in y divided by change in x when there's only one point. I get 0 over 0, which is undefined. We have to know what kind of 0 over 0 we're dealing with. So we think of a secant line by choosing a second point that's on the function, but nearby. We construct a secant line by choosing a second point from the function. So on the curve. We choose a second point on the curve, build a secant line, and say this is an approximation of our tangent line. Then we notice that this secant line sucks. I should choose a point that's closer to the given point. So then we start moving this tangent line, this second point closer. And this will improve our approximation. If we make those two, that second point closer to the first point, that's going to improve our approximation. And then we do the calculus thing. We consider what would happen if you move that point infinitely close. We're trying to calculate delta y over delta x. At our secant line. But we only get delta if we have two distinct points. We only will see change if we have two different points. So somewhere between the secant line where we have 2 points and 0 over 0, not helpful. I need red for that. What kind of 0 over 0 are we dealing with? And that's where we have all this derivative things. The tricky part, mechanically, is that we have these 2 points, and the second one is close to the first one. There's always a closer point. There's always a closer point. There is no next point. So we have to make some stuff up. We have to figure out what's going on. What 0 over 0 are we dealing with? Any questions? Leading into the rest of this stuff, the fourth, 1, 2, 3. Leading into the fourth part, area is equal to length times width. That's how we're going to use the framing device for area under a curve. So next step is to remind you of how we think about integration. Integration is multiplication, but one of the factors is continuously variable, which means integration is just addition, because addition is what we do when our terms are all different. Actually, multiplication is what we do when our terms are all different. Integration is what we do when we're trying to multiply and the terms are continuously different. But, follow for part 2. Any questions? People are going to be looking at the notes. They weren't here. Why are you saying that? We're just like zooming through it. See, the great thing about watching the videos later is that you can do the classic double speed. And it's like, oh, he's just babbling again. So you just like fast forward. 10 seconds, 10 seconds, 10 seconds. He usually babbles for 30 seconds before it comes back to the point. It's click, 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 and then back on point. All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.